Welcome to the Three Takeaways podcast, which features short, memorable conversations with the world's best thinkers, business leaders, writers, politicians, scientists, and other newsmakers. Each episode ends with the three key takeaways that person has learned over their lives and their careers. And now your host and board member of schools at Harvard, Princeton, and Columbia, Lynn Thoman.
Hi, everyone. It's Lynn Thoman. Welcome to another episode. Today, I'm delighted to be here with Danny Sigman. Danny is a geoscientist, that's an earth scientist, and a professor at Princeton. He studies Earth's climate over history. I first met Danny about 5 years ago in Amsterdam and was intrigued to learn that Earth's temperatures, even with the worst projections of global warming, will still be about 15 degrees cooler than temperatures were for millions of years. Antarctica even used to be ice-free, and with crocodiles. I'm excited to put the current issue of climate change into the historical context of Earth's climate over time, and to learn why it's not the increase in temperature that's the problem, but the rate of increase, how fast we are warming the Earth. Welcome, Danny, and thanks so much for being here today.
Oh, thanks. Thanks for having me, Lynn.
It is a pleasure. Danny, can you start by telling us what the greenhouse effect is?
The greenhouse effect is a process by which it becomes harder for energy to leave the Earth system and forces the Earth system to become somewhat warmer. Let me back up for a second. The Earth is constantly taking up energy from sunlight, absorbing sunlight. And if that's all that the Earth did, the Earth would just get warmer and warmer and warmer. So it must have a mechanism of also losing energy so that it's able to maintain a stable temperature. And the way that it does this is that it also gives off light. The sun gives off light, the Earth gives off light, but the Earth's light is in the infrared wavelength. It's a wavelength that we can't see, but you can see if you use an infrared camera. And what you see when you look at a photo from an infrared camera is that hotter objects are giving off more of this infrared light. And that's how the Earth regulates its temperature. It reaches a temperature that's appropriate for it to be giving off as much infrared light to space as it's absorbing from sunlight. At that point, it has a stable temperature. What does the greenhouse effect do? The greenhouse effect causes infrared light leaving the Earth's surface to be captured in the upper atmosphere, which causes more of the outgoing infrared radiation from the Earth to be coming from the upper atmosphere as opposed to the surface in the lower atmosphere. It's like putting a blanket over the Earth's surface, making it harder for it to lose energy and thus causing it to warm up to reach a new stable energy budget. Now, with regard to the greenhouse effect, we next need to ask what are the gases in the atmosphere that are delivering the greenhouse effect. Water vapor is the strongest greenhouse gas. However, water vapor in the atmosphere is very tightly tied to the atmospheric temperature. It can amplify temperature changes, but it can't instigate them. The next greenhouse gas on the list, the next strongest, is carbon dioxide, and it can change independently of atmospheric temperature. We really think of it as the driver of the greenhouse effect. Of course, what we're going to want to talk about is the role of the greenhouse effect in ongoing global warming. But before we get there, I just want to point out the natural greenhouse effect is a great stabilizer in Earth's climate and critical to Earth's habitability. If we had no greenhouse effect, the Earth would be frozen over and there wouldn't be life really as we know it. If we had the greenhouse effect as strong as Venus, well, then we'd have a temperature similarly as high as Venus. And again, we'd have an uninhabitable planet. We have just the right greenhouse effect, that we have a liquid water-rich system that's habitable for life as we know it. And you can ask, well, what is the mechanism that gives us just that right greenhouse effect? And looking into Earth history that we figure out how this works. Geologic processes regulate atmospheric temperature through the concentration of carbon dioxide. Exactly how this works would take us a little bit too much time to go through. But this is the reason that the Earth has been habitable for millions and billions of years, and why once life was discovered on Earth, it's been able to continue in an unbroken chain to the present. The point here is that the greenhouse effect is not something that has just become relevant. It's always been central to how we think about climate. One caveat that I need to make here is that this regulation of climate by the greenhouse effect requires long time periods, hundreds of thousands of years or longer. It can explain the long-term habitability of Earth, but it can't prevent rapid climate changes from occurring.
What's the connection of carbon dioxide to the greenhouse effect and global warming?
We need to start with the fossil fuels. Fossil fuels are fossil plant or algal material that was generated by photosynthesis at some past time on Earth, has been buried in rocks and altered in a way that it's greatly increased the energy density of this material and makes it a wonderful fuel. Humans have used the fossil fuels, coal, petroleum, natural gas, to drive modern society. The consequence of that fossil fuel use, though, is we're burning that organic matter, converting it to carbon dioxide. That carbon dioxide acts as a greenhouse gas in the atmosphere, strengthens the greenhouse effect, and drives warming.
Why are we so sure that it's the greenhouse effect that is causing global warming?
First of all, we know that there's warming. We can measure it well. Two, we know that carbon dioxide concentrations are rising in the atmosphere and that rise is due to this fossil fuel burning I described. Three, the other possible causes of warming over this time period can be ruled out. So really, by process of elimination, we just have the greenhouse effect left. If we do either simple calculations or use complex computer models, we see that the amount of CO2 rise and the resulting expectation for strengthening the greenhouse effect can explain well the warming that we have seen.
Will global warming push Earth to unprecedentedly high temperatures?
Not with regard to Earth history. If we go back, let's say, to the age of the dinosaurs, about 100 million years ago, Earth's climate was much warmer. There's abundant fossil evidence for all sorts of reptiles and dinosaurs at both poles, ferns and other types of plants at the poles. It was clearly a much warmer Earth. And in fact, that temperature is the temperature that's characterized much of Earth history, that warmer temperature. Since that time, over about the last 50 million years, climate has been cooling gradually. 35 million years ago, we started having ice on Antarctica. About 3 million years ago, we started having ice in the northern hemisphere. We actually exist in a relatively cold time in Earth history. Even the most pessimistic estimates for how much warming it will cause will just bring us part of the way back toward that warm condition that, for example, existed during the age of the dinosaurs, and that is sort of more typical of Earth's environmental condition. Now, I have to make the caveat that while this might be the more typical temperature, all life on Earth right now is used to the climate that we've recently had, not that climate necessarily of 100 million years ago.
Danny, to put this into numbers and temperatures, how much warmer was it on Earth compared to what it is now and what it will be in the worst case of global warming?
Reasonable global average temperature difference is about, as you said, for the age of the dinosaurs, 20 degrees Fahrenheit or so warmer. Now, we have to appreciate that the temperature changes aren't uniform across the globe. The latitudes close to the equator, the temperature changes less as global climate changes. The polar temperatures change more as global climate changes.
Danny, can you give us an example with one species, how it evolved with Earth's climate?
Climate has been cooling over the last 50 million years or so. The story of horses is tightly tied to this. The ancestor of horses back 55 million years ago, Sivorhippus, was about the size of a large house cat. Over the 50 million period, as climate cooled, forests shrank in their extent and grasslands grew. We believe that this is responsible for what we observe in the fossil record, which is an extraordinary increase in the size of horses and the development of a number of traits that work in grasslands. Large teeth that wear out over the course of life, large body sizes to protect oneself in an open ecosystem, speed to protect oneself, long necks to be able to be grazing on grasses as opposed to getting food from shrubs or trees. All of the features that we see in modern horses really speak to this climate evolution from warm and wet conditions in the early part of the last 50 million years to cooler and drier conditions thereafter.
Temperatures, even with the worst projections of global warming, will put the Earth about 5 degrees or so warmer compared to 20 degrees or so warmer, which Earth used to be for much of its history. Is that correct?
That's correct. The global warming science is always a complex discussion with regard to uncertainty and what pessimism really means. For example, we could imagine a global warming scenario that would be as much as 8 degrees C by 2300. That would be something that's more approaching that warmer temperature level that characterizes more of Earth history. But yes, from most expectations, we're only going to be working a part of our way back. We'd still be in a relatively cool Earth in a geological perspective.
Why are we so worried about global warming?
2 reasons. The first I've already mentioned, which is that the ecosystems that are on Earth ourselves, we're adapted to the climate that we've most recently had. That's, I guess, the more relevant starting point to some degree. The bigger reason, the second reason, is that the rate of warming is just extraordinary. This rate of warming means that we really can't adapt quickly enough to the changes in climate. And that warming will be continuous. Every time we might hope to change things to bring them to the new temperature, we're going to find that the temperature has gone up yet further. We'll be chasing climate.
How will things change? What types of negative impacts do you see with global warming over the next 40, 50 years?
We can break this down into the following categories, and we'll run through each quickly. Temperature itself, water, ice, and ocean. Okay, so first let's start with temperature. Global warming will cause the temperature zones on Earth to move away from the equator and toward the poles. And so, of course, both human activities that require that given temperature will need to move poleward, and natural ecosystems will need to move poleward. And many species, and thus ecosystems, will not be able to migrate quickly enough. And that will lead to massive ecosystem disruption and similar consequences for things like agriculture. Not only will sort of the spatial patterns of temperature change, but the temporal patterns will change. Spring and fall will change in their timing. This will wreak havoc for both human activities and for natural activities like flowering and pollination of plants and things like that. Temperature extremes, warm temperature extremes will become longer and more intense. So longer heat waves, more intense heat waves. Moving on from temperature alone, just having thought about temperature, we also have to think about precipitation, because this really matters, water availability at the surface of the Earth. The expectations are that the high latitudes are going to get wetter. For the lower and mid latitudes, it's going to be a more complex pattern, with dry places tending to get drier, wet places tending to get wetter, and dry times tending to get drier, and wet times tending to get wetter. And what this means is, on the one hand, stronger storms, stronger events like hurricanes. On the other hand, longer drought periods. And we can really see these types of predictions playing out, for example, in the wildfires of the West over the last couple of years. That's precipitation. The warming of the ocean in itself causes sea level to rise, and the melting of polar ice caps causes sea level to rise. So sea level will be rising. That means for coastal communities, many more flooding events per year, eventually to the point that it's no longer tenable to be in those regions. And the ocean also has impacts. For example, coral reefs will do very poorly dealing with surface ocean warming and with the change in ocean chemistry associated with the rise in carbon dioxide.
Danny, this will all happen over the next 40 or 50 years?
This will happen in a somewhat accelerating form over the course of this century, is most people's expectation. By 2100 or somewhere in that next century, depending on, the thing that this depends the most on is how much fossil fuel burning humans carry out when we start to curtail that burning, what that schedule is. But many of the predictions have accelerating changes over this century, then somewhat decelerating over the next century, and sort of stabilizing over the next couple of centuries at a new higher temperature.
What are the greatest unknowns about global warming?
The biggest unknown, and I've just mentioned this, is human activities. What humans are going to be doing, how much carbon dioxide we're going to be emitting to the atmosphere. We are the number one control over how big a problem global warming is, and that's a key message. In terms of predicting how much climate will change and what the impacts will be for a given amount of carbon dioxide emissions, the challenge for the science is the fact that even though the controls on climate are very few, there's really just a small number, basically 3, those 3 controls can interact with one another, what we refer to as feedbacks. To give you an example of an amplifying feedback that takes in a given amount of climate change and gives you even more. Ongoing warming is melting ice at the surface of the Earth. That's allowing the Earth's surface to absorb more sunlight than before, which is then causing further warming. We know what many feedbacks are, but we don't necessarily know how strong they are, how sensitive they are. And then there are probably feedbacks that we haven't yet identified. These are really difficult to account for in our uncertainties. Now, to be clear about uncertainties, they may make the problem less bad than we think, but of course, they may make it worse.
Danny, last question. What are the 3 key takeaways that you'd like to leave the audience with today?
Yeah, as we were talking about Earth history, one of the reasons for doing that is to get across the idea that the greenhouse effect is not a speculative idea or an idea that's just become relevant under global warming. The greenhouse effect is central to Earth's climate. The predictions about global warming are more robust than many people recognize. The second thing I would point out is that the greatest concern with global warming is the rapid rate of change. If we had a slow rate of change to a new climate, we would have time to adapt. Things are happening too quickly, and that's a huge problem both for humans and natural ecosystems. And finally, after multiple thousands of years have passed, the Earth will have more or less returned to its climate before the human global warming experiment. The key message, I think, for us about this is that global warming doesn't reveal the vulnerability, the fragility of the Earth. The Earth is incredibly robust, in fact. What it reveals is the fragility of humans and their reliance on the environment and on natural ecosystems.
Danny, this was great. Thank you so much.
Thanks very much.
If you enjoyed today's episode and would like to receive the show notes or get new fresh weekly episodes, be sure to sign up for our newsletter at 3takeaways.com or follow us on Instagram, Twitter, and Facebook. Note that 3takeaways.com is with the number 3. 3 is not spelled out. See you soon at 3takeaways.com.